are super excited to have Cynthia Rudin here today to give a talk entitled Almost Matching Exactly. Cynthia is a professor of computer science, electrical and computer engineering, and statistical science at Duke University, where she directs the Prediction Analysis Lab, whose main focus is on interpretable machine learning. She is also an associate director of the Statistical and Applied Mathematical Sciences Institute and a fellow of both the American Statistical Association and Institute of Mathematical Statistics. Previously, Professor Rudin held positions at MIT, Columbia, and NYU. She holds an undergraduate degree from the University of Buffalo and a PhD from Princeton University. She's a 3-time winner of the Informs Innovation Applications in Analytics Award, as well as named one of the top 40 under 40 by Poets and Quants, and was named by Business Insider as one of the 12 most impressive professors at MIT. Cynthia, welcome to Oatmeal.
Thank you. So I'm going to discuss work with the AME lab at Duke, which is almost matching exactly. And it's run by 3 professors. It's me and Alex Volpovsky and Sudeepa Roy. And Alex is an expert in causal inference, and Sudeepa is an expert in databases. So it's nice to work with a kind of diverse group on this. Okay, so our goal is to determine conditional average treatment effects from observational data. Now, observational data is not like clinical trial data where treatment is randomized. It doesn't come in pairs of identical twins. You just get a whole pile of people, and you might want to figure out how to match them so that the match groups look kind of like identical twins, so that you have some control and some treated units in each group. Now, if you're going to do matching and you have high dimensional data, then you run into this problem that you can't find identical matches since there are no identical twins. So most of the time, because most of the time people are not exactly the same, right? They differ on at least some dimension. So you can't match people on all the covariates. You have to pick which covariates to match on. Now, as long as the things they differ on are not important, you're good. So here, they're all wearing different things than their partners, right? So it's still okay to match them as long as you're looking at things like health conditions where what you wear doesn't actually matter. But in general, you want to match on as many good covariates as possible. But picking which variables to match on, that's actually tricky. And that's what our lab works on, is constructing high quality match groups so that we can do causal analysis. And once you have these high quality match groups, you can take the treatment outcomes, you can take the outcomes from the treatment units and then subtract them from the outcomes for the control units to get an estimate of the conditional average treatment effect. And then if you want to, you can use a machine learning method afterward to kind of smooth those estimates out. All right, now we're in the most basic setting of the potential outcomes framework, where there is a vector of covariates, which is like patient data, and then Y is outcomes, which, in this case is a stroke, and then T is the treatment. That's whether the payment, it's like a 1 if the patient got a treatment, 0 if they didn't. And so in that case, it might be a drug. And we want to do matching. Okay, so why matching? Well, matching is interpretable. You can examine the data in a really fine-grained way and determine whether the matches are valid or whether you're missing any important variables or whether you have data quality issues. Like when you're making a causal conclusion, right, that's important. You don't want to mess it up by trusting a black box on a messy data set. And every large data set I've ever seen is messy. Now, most matching methods don't try to match exactly. And most matching methods use a fixed distance metric between units that you have to pick before doing matching. And the problem is that humans are not very good at constructing high dimensional distance metrics in their heads. So what's different about this work is it actually tries to match exactly on as many good covariates as it can. Okay, so I'm going to be spending most of this lecture discussing the almost matching exactly framework, as well as our kind of main algorithm, which is it's the flame-dame algorithm combination. And this is for large categorical data sets. We have other algorithms for mixed data sets that I'll talk about later in the talk. And I just have a snapshot here of our of the website for our documentation. And you can just go to that and browse it if you're interested. Okay, so as I mentioned, our goal is to match treatment and control units almost exactly. And there are 2 main kind of important elements of the flame-dame framework. Now, for any given treatment unit, you have to match with at least one control unit. And so for us, we're going to try to match exactly on the largest set of good covariates that together can predict the outcome well. So what does good mean? Well, for us, it means that if you take those covariates together, that they can predict the outcome well on a holdout training set using machine learning. So the prediction quality, like the goodness of a set of variables, is determined from machine learning on a separate training set. And then the other really important thing about this particular algorithm is it scales. It works with big data sets thanks to a combination of bit vectors for one implementation and database queries for another implementation. And so I'll be going over how all of this works. Okay, so the new patient comes in. We want to estimate the treatment effect for that patient. And then the question is, which control units should we match her to? So we ask the algorithm, and it says, you should match on covariates 9, 2, 3, 14, and 6. Well, how do you know that those are the right covariates to match on? Well, it's because a machine learning model with those covariates predicts the outcome well on a training set. And also, there's a control unit in her match group that she matches to. Okay, so this is the outline of my talk. I'm going to go over very briefly some related works, talk about how the algorithm works, and then go over some of our other algorithms for continuous and mixed variables. I won't go into detail about those other algorithms, though. I'll just kind of skim the surface on those. Okay, so there is a large literature on matching methods. I'm providing a very incomplete summary here that captures, I hope, at a high level, the main themes of matching. There are really two flavors of matching methods in the literature. One is projection methods that project the covariate space down to one dimension, like propensity score matching or prognostic score matching. And those ones are not interpretable, as I'll show you in a minute. They match units together that are totally different from each other in covariate space. The other methods try to balance overall statistics of treatment and control groups to get average treatment effects. And they always use a distance metric that was chosen beforehand, which really isn't a good idea. Now, as far as we know, no prior work in matching considers learning the distance metric from a training set, which is what we're doing. And most work produces uninterpretable matches that I'll show you. Now, it's not like the idea of trying to create exact matches is new. I want to draw your attention to a section of Rosenbaum and Rubin from 1983 that deals specifically with the type of matching that we consider. So they note that as a method of multivariate adjustment, subclassification, which is matching, has the advantage that it involves direct comparisons of groups of units that can be both understandable and persuasive. Okay, so they note that subclassification involves direct comparison. So they're trying to match like units and compare them. And that's what we would like to do, match and compare. And most importantly, they reaffirm that this is understandable and persuasive, which we think are some of the most important qualities of matching algorithms. They're intuitive, they're uncomplicated, they're reproducible. And these guys, they wanted to do exact matching, but they couldn't. They had to reduce the dimension somehow because they ran into exactly the same issue that I just talked about. So when you're trying to match in high dimensions, when you do that matching, most subclasses won't contain both treatment and control units because you can't find exact matches. And so you have to reduce dimension. So because if the matches are empty, you can't draw any causal conclusions. Now, briefly, let's talk about the quantities that individuals want to study. So ATE is traditional. This assumes that you want the average treatment effect on everyone, but that's not what we're considering here. We want the treatment effects on individual units. We want a treatment effect given your covariates, the conditional average treatment effect, or the CATE. We want a treatment effect for you, not a treatment effect for the average person. Okay, so why can't you just use propensity or prognostic scores? And as I mentioned, the reason is because the matches are uninterpretable. And I want to show you an example. So here, this is probably the result from probably the most overstudied data set in causal inference. This is the Lalonde study. And here your goal is to try to predict the effect of a treatment on income in 1978. And here are your covariates. Now, let's see what happens when we match on the prognostic score. The prognostic score is the probability of outcome under control. So this is a unit that I want to match to. He's 22 years old, 9th grade education, not Black, is Hispanic, not married, doesn't have a degree, no income in 1975. So we asked for people with prognostic scores like his, and we find all these people that have similar prognostic scores. These are the nearest neighbors, but some of them don't look anything like him. Like this person's 30, this one's 44. Some of these people have completed high school. One of them's married, and a bunch of them had income in 1975. So it's not an interpretable match group. And I want to contrast this with a match group from one of our approaches that I'm going to show you, that I'm going to talk about a little bit later. So here again is the same treatment unit, and here is the match group. And as you can see, everybody has almost the same age, almost the same level of education. So between 8th and 10th grade education. The race is mixed, but that's because the algorithm decided that race wasn't actually that important. And so it decided that it didn't need to match exactly on race. And nobody's married. None of them have a degree, and they didn't have any income in 1975. So it's visually, this match group is substantially more internally consistent. And that's what we're trying to do. Okay, so the motivation, of course, why can't you use propensity prognostic scores? Because they produce uninterpretable match groups. They put together people in the covariate space that have nothing to do with each other. So why can't you just choose a distance metric and match on that? And this really isn't a very good idea. It's just not reliable. Like, humans might include a bunch of irrelevant covariates to match on, and the whole process isn't reliable. Like, different analysts, different humans would just do this differently because they would construct a different distance function. And here we want high quality matches, right? Asking humans to create these distance metrics is like asking humans to do machine learning in their head. Okay, so with that introduction, I can go on to introducing the formulations and the algorithms. Okay, so there are two data sets. There is the matching set, where we're going to do matching, and the training set, which we use to figure out which variables are important or not important. That's all the training set is used for, is figuring out which variables are important. So it doesn't matter exactly what we do on the training set, as long as we kind of figure out the importance of variables. And then what we want is, for each unit, we want its match group. So theta, I haven't told you what theta is, but theta is an indicator for which variables to match on. So for each unit, we want its matched group for variables theta in the matching set, which consists of all of the units in the matching set that are matched with I. Okay, so for each unit, you want its match group. Okay, so let me introduce kind of the formal notion of the framework here. Okay, so actually, first let me restate what I had in the previous slide with a little more notation. So theta is the variable selection indicator. It tells you which variables you're going to match on. And the match group for unit I with those variables from the matching set is the set of units in the matching set, such that they agree exactly with I on the variables defined by theta. So I'm going to give you an example here. So let's say that theta says that we're going to match on variables 1, 2, and 5. And this is my unit. What that means is I only pay attention to variables 1, 2, and 5. And every unit that's matched with xi is identical to it on variables 1, 2, and 5. And it doesn't matter what's in the other variables. Okay, so hopefully you understand what this notation means now. And if you know theta for that unit I, that is sufficient to define its match group, because all you have to do is find all the units in the matching set that agree exactly with unit I on those covariates defined by theta. So what you're trying to find for each unit is the special theta that defines its match group. Okay, now the training set, as I mentioned, is just used to figure out what theta is, just used to figure out which variables are important. And the way we do that is by, again, using a machine learning method on a holdout training set. And we evaluate the quality of a set of variables by running machine learning on that holdout training set and looking at the error, So if theta has a low prediction error, it's okay to use for matching because it means you have enough variables that you're matching on that you can predict the outcome well. Our rule of thumb is that we should really stay within 5% of the minimum error rate. So 5% of the error rate that uses all the covariates, right? So if you run machine learning with all the covariates, you get some number. If you are worse than 5% above that, we say, okay, that set of covariates is not good. So we always try to stay within that 5%. And it's just a rule of thumb. You can change it if you like. It's a parameter. Okay, so what we're trying to choose is the set of variables such that it minimizes the predictive error on the training set, and we can find a control unit in the match group. Okay, so this term involves the training set, means the variables are predictive. This term involves the matching set, says there exists a control unit in the match group. So I'm just going to go over that last statement again because it's kind of confusing, but it's actually the most important equation I have in this whole talk. All right, so for treatment point I, we want to find the set of variables that together can be used to minimize error on the training set such that there exists a control point in the matching set that matches on those covariates. Okay, do I have any questions at this point?
I think that seems pretty clear to me. So for a given individual, minimize the loss on your training set, so your accuracy of predicting Y, under the constraint that you need one member in the control group.
Yeah, that's right.
I think, yeah.
Goes wrong if you use just one set. Well, there's a bunch of things that could go wrong if you use just one set, because then you might have to reduce dimension all the way down, and you wouldn't be getting the best matches for people. Like, let's say that you could find identical twins in the original data set. Then you would just want to match those people on their identical twins, right? You wouldn't want to use the same set of variables for everybody, because then you'd be ruining your chances to sort of capture these very, very good matches you could get earlier on. And then another thing that goes wrong is that if you have units with missing data, so if some of the variables are missing, you might not be able to match units really well on the same single set of variables. So we kind of want to for each unit, we want to match them with somebody using the best set of variables we possibly can. Okay.
I have another quick question. So what's the interpretation of the 5%? Like why allow for why cut off a solution if it violates that tolerance in the error rate?
Because you really just don't want bad matches. Like if you match units together on like a couple of variables and just ignore all the rest, that's not a good match group. It's not interpretable, and it's just not going to give you high quality estimates of treatment effect, because again, you're then matching people who disagree on some important variable, and you don't want to do that. Okay, sorry, I answered the other question wrong. One data set, not one set of covariates. I'm sorry about that. Okay, so you can't merge the training and matching set because it's not what's called honest. If you use the outcomes to figure out how to match, then you don't actually have honest estimates of the treatment effect, because you could simply be matching people that have similar outcomes together, and you can bias the result. So that's why you really need to have a separate training set. I mean, there are some like machine learning methods that try to use the same training and matching set, but there's a problem with this honesty. Okay, so since the data is high dimensional, is it practical to train a machine learning model for every choice of theta? Ah, ha, ha, ha. Now, yeah, so we're getting there. We're getting there. That's a very good question, and I will be answering that. Okay, so you're getting to what the algorithm actually does here. So for the first task, can't you do a covariance ranking based on some error criterion to select the variables? Yeah, so that's what we're going to do. But it's going to be different for Dame and Flame, and it's actually well, you'll see how it goes. Well, I'll show you. Yeah. So these questions are good. They are implying that I should continue with my talk. Cool. Question: are we still in the process of choosing the theta? Yes. I thought the theta has been chosen in the training set. Yeah. So the theta we want is the one that solves this equation, and we have to solve this thing for all of the units. And so it's a very computationally expensive task to think about solving all of these problems for all of the units. And so I'm going to show you an algorithm that solves them all at the same time. Okay, let me keep going because a bunch of the questions are basically indicating that they want to know exactly how this algorithm works. All right, so the first algorithm I'm going to talk about, the main one, is called FLAME, or fast, large, almost matching exactly. And the algorithm starts by doing exact matching on all the covariates. So find as many identical twins as you possibly can. Now, the subroutine we have for doing this is called basic exact match. Basic exact match, all it does is it finds identical twins on a set of covariates. You hand it a data set, you hand it theta, and you say, find me all identical groups with respect to these covariates. We have two implementations of basic exact match. There's a bit vector implementation and a database implementation. The bit vector implementation allows this computation to work very quickly in memory. And then the database one allows it to work on data sets that are so large that it doesn't fit in memory. And the fact that we have this subroutine working so quickly is the key to the algorithm. Okay, so once we've run basic exact match, we go to the training set and we say, which covariate is the least important for prediction on that training set? The way we figure that out is that we run, well, there's a couple of ways you can do it. You can run the machine learning with and without that variable, or you can, use variable importance techniques where you scramble the variable and see if the error changes, or you can do linear regression and look at the coefficient that is the smallest. Okay, so all you have to do, though, is identify a covariate that's not important, and then you eliminate it. And then you repeat. You run basic exact match again, find as many match groups as you can, and then go back to the machine learning, eliminate another variable, run basic, and then go back and run basic exact match again. You just keep doing this, okay? And so it's a backward elimination procedure. And eventually, you'll get to the point where the remaining set of covariates can no longer be used to predict the outcome all in the training set. So in other words, your error goes above 5% above the minimum. And at that point, you stop and you say, I cannot match the rest of the data because they're outliers. They're actually too far away from another unit in the variables that matter, and I can't match them. So you're kind of doing the least harm as you eliminate the covariates one by one. Now, Dame is the sister algorithm to Flame, and Dame has a pretty similar outline except for kind of a key point. Dame starts by exact matching on all covariates, again, by running basic exact match. But this time, instead of eliminating the least important covariate, it eliminates the least important subset of covariates that has not yet been eliminated, using machine learning on the training set to figure out which subset to eliminate, and then it puts it back afterward. So it's doing kind of like a backward closure type algorithm. And so it has this nice monotonicity property. And then it's repeated each time. So as you can see, that Dame is much more expensive than Flame, because Dame is solving a combinatorially, it's got a combinatorial number of possibilities to consider, whereas Flame is doing backward elimination. And so Dame produces higher quality match groups, but computationally it's slower. So what we found is that doing a combination of Flame and Dame is actually really efficient, because what you do is you start with a bunch of, tons of covariates, most of them being irrelevant. and then you run flame and eliminate variables until the number of covariates is small enough to run DAME, and then you run these expensive DAME iterations. So I'm going to give you an example to show you how this works. So let's say you have a data set of 40 covariates, only 9 of which are relevant. Now, we're going to run basic exact match to find all the identical twins, and then we will then go to our machine learning and say, which covariate can we eliminate? And it'll say, covariate 40, you can eliminate covariate 40, it's not important. So then we match on 1 through 39, and then those guys are done. And then we go back to the machine learning and say, okay, we still have units to match. What do we eliminate? And it says 39. Say, okay, great. Then we keep doing this, keep eliminating and eliminating until we get down to a data set that's small enough that we can run DAME. And so at that point, let's say we've eliminated variables 40 through 11, and we're down to variable 10. And the machine learning says, okay, you can eliminate variable 10. All right, we eliminate variable 10, but then we put it back, right? We eliminate 10, we match on 1 through 9. We put 10 back, and then we say to the machine learning, okay, we've already eliminated 10. What should we eliminate next? And it says 9. So we say, okay, fine. So we'll match on 1 through 8 and 10. Cool. Then we ask it again. It says 10 and 9. Because you can't eliminate 10 and 9 until you've done 10 and then 9. And then we put those back. And then it says, okay, you can eliminate 8 now. Then 10 and 8, 9 and 8, 10, 9 and 8. So as you can see, you can't eliminate 10, 9 and 8 until all subsets of it have been eliminated. And then those are the DAME iterations. And eventually, after we get down to it, it says, I'm sorry, I have to stop now because I can't eliminate anything else. If I eliminate anything else, I can't predict the outcome. So I need to keep variables 1, 2, 4, 5, whatever is left in here. Okay, cool. So let me just answer a couple of questions here. I'm wondering about the connection with local regression, which is almost done in low dimensional settings, as far as I know. I guess there must be some connection, but it'll depend on how the algorithm works. I am not sure what that connection would be. I am sorry. We sometimes do regression within the match groups, but I'm not sure I see the connection. There could be one. Okay, so feature selection complexity could be 2 to the p-1, which is too much. I agree. And so that's why we do this flame DAME combination and use this backward closure property to help eliminate variables in an order that isn't so expensive. And the backward closure thing is used in data mining algorithms all the time for solving these kind of combinatorial problems where you're trying to find like rules that involve combinatorial, combinations of the features. Yeah, I know what local regression is. I just don't understand how how matching is exactly related to local regression. I mean, you're doing kind of like a piecewise local constant, right? But because each match group you can think of as a collection of covariates, but the problem is that it's like overlapping and stuff. So well, what you would do at least after you get the match groups is you might do regression for the treatment effect afterward, like a local regression for the treatment effect afterward to try to estimate treatment effects more smoothly, I guess. Okay, what is the prediction regression model that's used? Oh, it does. I'm not talking about how to exactly do that smoothing that I just talked about. You can use any machine learning method. Oh, you're talking about inside the training set. So inside the training set, you can use any machine learning method you like. We tend to use either linear regression for like really huge data sets or boosted decision trees for smaller data sets. But as long as it can identify what the not very useful variables are, then you're good. Yeah, and it's trained as usual. It's trained, you can use your favorite, boosted decision trees or whatever you want. Cool. Okay, great. So now I've talked to you about how it works. Let's talk to you about how it performs. And I learned a lot from when we did this experiment. The first time we did this, I had no idea what I was in for, to be honest. Okay, so now with causal inference, you never have a treated and a control unit in real data that are identical. Like you never have a data set where you actually have the treatment effect. So you have to do simulations. So we created a simulation that has 10 relevant covariates, a linear baseline term, a linear treatment effect term, and a quadratic treatment effect term. And the quadratic treatment effect term is placed there so that linear models won't do well. Okay, so you should be expecting that. There are 20 irrelevant covariates, meaning that they don't contribute to the outcome, but they're in the database. Now, we made it more difficult by introducing some non-overlap. For the 10 relevant covariates, everything overlaps beautifully. But for the irrelevant covariates, then if you're in the control group, you have mostly zeros for all those irrelevant covariates. And if you're in the treatment group, you have mostly ones. So what that means is that if the algorithm doesn't figure out that the irrelevant covariates are irrelevant, it's going to have a hard time matching on them. But if the algorithm figures out to eliminate those covariates, then it can match really well and you get good overlap between treatment and control, and the algorithm can succeed. And that's why Flame is going to do well here, because it's going to use machine learning to figure out that those irrelevant covariates are irrelevant and eliminate them. Now, for this experiment, 10% of the data was used as the holdout. There's 20,000 total units, half treatment, half control. And there is no noise, which means that if we match exactly, we get the exact correct answer. So you should not be surprised then when I show this plot that shows estimated versus true, so predicted versus true, and you want to be on the diagonal, and so we're right on the diagonal, so it's not a surprise. And then it should also not surprise you that if we do one linear regression on the treatment group and one in the control and subtract them to get treatment effects, that it won't work. And it doesn't work because we have a quadratic term in the outcome model. So we misspecified the model. And my point isn't that, look, misspecified models perform worse, which is obvious. But my point instead is that parametric models are pretty much always misspecified. The nice thing about Flame, even when the predictive model on the training set is wrong, we didn't have to rely on that parameterization. We just had to get the relevance of covariates vaguely correct because matching is non-parametric. You don't have to worry about the kinds of issues that arise with doing double regression. Now, we tried experiments with a bunch of the major packages that you can download to do matching, and this is where I was really surprised. So this is Flame again. This is where we stop it early. As usual, at that 5%, special 5% rule of thumb. Okay, if we run it all the way to the end, we get some crappy matches. Okay, but I want to point out the range, which is -25 to kind of 25, somewhere around there. This is GenMatch, which is genetic matching. As you can see, genetic matching clearly is not designed for estimating average treatment or estimating conditional average treatment effects. It's only designed for average treatment effects. So it matches people together that have nothing to do with each other. So this is really not a surprise. This is Mahalanobis distance matching. And these are variations of propensity score nearest neighbor matching. These oracles are where they actually knew which variables were important. So fine, none of these methods are, these are all matching methods. None of them are actually designed for estimating Kates. Okay, so what about machine learning methods? There's a bunch of very, well-used causal machine learning packages. This is causal forest. Now, random forests in general are unable to handle irrelevant covariates. And so causal forest inherits that property. I don't know if you can see this, but the range of true treatment effects here is 0 to 30. And even we have a little noise, and that's within 0 to 30. This package was estimating causal effects that were an order of magnitude off. And we tried to troubleshoot it. I even have a former student who works on the package, and so I was asking her for help. But what ended up happening was that we just ended up giving up because troubleshooting black box models is exactly not fun. It's exactly why we're doing this project in the first place, is because it's not fun to troubleshoot a black box model. This is BART, which is Bayesian additive regression trees, which is the best black box method out there for causal effects, and it does a brilliant job. And then CTMLE, which is targeted maximum likelihood, has some noise in there. Okay, so now you understand how it performs. It performs on par with the best black box models in terms of Kate prediction accuracy, and yet it's interpretable. Okay, so how does it scale? Well, here I'm showing a bunch of different matching methods on the data set I just showed you, which has 20,000 units and 30 covariates. That's not particularly impressive because they all finished under a minute, except for these two, which use integer programming. But the data set that I'll show you on this side of the screen has 1.2 million units and 59 covariates, and everything here crashed or took more than 10 hours, except for the database version of Flame, which took an hour and a half. And as I mentioned, that's because the database version can handle data sets that are so big that they don't even fit into memory. And by using database queries for basic exact match, it runs very quickly. Okay, so I want to show you an example of the kind of results that Flame produces. This is a result on the Natality data set, which has it's a very large set of birth data about births. And your goal is to estimate the effect of smoking, the pregnant woman smoking, on the risk of abnormal health outcomes for the child. No, it's not the fetus smoking, it's the mother smoking. So anyway, it's 10 cigarettes per day is the treatment. Control is no cigarettes. The outcome is birth weight, and this is the number of units at 2.1 million, and then 75,000 of them are treated, and here are the covariates there. And what we found were plots like this. So this is estimated treatment effect, and this is the number of units in the match group, and each dot is a match group. So what you can see here is that the birth weight definitely seems to be impacted by smoking because the treatment effect is negative. And the results become more trustworthy as the sizes of the match groups get bigger. So if you have these are small untrustworthy match groups, and these are large trustworthy match groups, and you can see that at some point, there's barely any match groups that are above zero. All of the match groups, the treatment effect is below zero. And so the results for this particular study are pretty consistent. There were other things we tried to investigate where the result wasn't quite so clear, and then we can say, look, you need more data on this topic because we're not seeing this consistent result among match groups. Okay, so far I've talked to you about Flame and Dame. Flame is the only method for adaptive, interpretable, very large scale matching. Dame computes higher quality match groups, but at a computational cost. And there's a bunch of stuff that I left out of the talk. And specifically, there is some theory that shows how you can estimate average treatment effects of Flame. It can calculate directly in specific settings. Now, a bit of so a good thing about this theory is that it shows that in specific instances, one doesn't expect to lose anything when compared to propensity or prognostic scores in terms of estimation of ATE, simply because you're using something like Flame or Dame. Other things I haven't told you is that we've extended Flame to networks data where the SITVA assumption is violated and units are actually talking to each other. And we've also extended it to instrumental variables. So if you are interested in those topics, you can check that out. Now, I want to spend the last part of the talk just discussing some of the other algorithms that we have, which are for continuous variables. So if you go to the AMA website, you'll see 4 packages. And I've talked to you about these two. And so now I'm going to just very briefly introduce those two without talking about the theory or the details of how they work. So the first method here, continuous covariates, they present a surprising challenge to the notion of exact matching because you can't do exact matching for continuous variables. You have to do some sort of almost exact matching. And so that's why we want to do this. And so we have two algorithms. One creates boxes and one creates ovals. So so adaptive hyperboxes, you take the treatment unit and you make a little axis aligned box around it. So that's AHB, and then mults, it stretches the variables so that instead of making like a little circle around, normally you'd make a little circle around the treatment unit, but since you don't know which variables are important, that's not a good idea. So what you really should do is kind of stretch the covariates that are important, squish the covariates that are not, and that will help you create a more reliable match group. Like you want to match really closely on age, but you don't want to match closely on race or something like that. Okay, so just a little more detail about adaptive hyperboxes. If you try to okay, so let's consider the simple task. So we have a potential outcome under control, which is this guy, and it varies with respect to this covariate, but it varies slowly out here and it varies quickly over here. And what that means is that these two guys, which probably should be in the same box because nothing's changing out here, they're in different boxes, whereas these two guys, everything's changing over here, so they really should be in different boxes. So this is the kind of thing that AHB does. It'll actually place these into different boxes where the treatment under control is changing rapidly, and then where it's not changing, it'll kind of make these bigger boxes. Okay, so how do we actually do this? Well, AHB starts with BART. It starts by running BART on a training set to get estimates of treatment effects, which are shown in these shades of blue here. And then it tries to construct these boxes that have specific qualities. Okay, so by the way, BART is run on the training set, and then we then make the boxes on the matching set. Well, we make the boxes on the matching set based on the information from the training set. And so as you can see, you can see it changing kind of gradually here. And so the boxes try to respect certain things about the BART estimates. They try to minimize the disagreement of Kate estimates with respect to BART. They try to be low variance with respect to the BART estimates. And they try to have a large support. So you want each box to be as big as possible. So you can see that because it's sort of relatively constant out here, the boxes kind of stretch along here and stretch along there, where things are not changing as much. And there are two formulations for AHB. There's a MIP formulation, which can run in parallel for each unit. So each unit gets its own MIP formulation, or each unit, you'd have to solve a MIP for each unit separately, so it parallelizes. And there's also some approximate formulations. So I'm just coming back to Lalonde one more time. And this picture describes 5 match groups from the Lalonde data set that are projected onto one dimension. And it's hard to see them, but they're kind of like this. And you can see that the structure of the response surface shows that things change a lot more rapidly in here when the response surface is changing a lot than out here where it's really not. And then MALT is the algorithm that produced the result I showed at the very beginning, where it stretches the covariate space. And here, Maltz found that age was really important to match on, so it matched really closely on age, so it stretched out the age variable. It stretched out the education variable as well. It tried to match as closely on education as it could. It just compressed the race variable because it thought race wasn't important. And then it was able to match these other variables anyway, because even though those variables weren't that important, it was able to find units that, that matched with those variables anyway. But I think income was actually important, so it did stretch out the income variable here. Okay, and matching, and Maltz also is quite accurate. It's just as accurate as all of the other black box machine learning methods, but it's not black box. Okay, so I hope your main takeaway from this talk is that matching methods are extremely powerful, not just because they're non-parametric, but also because they're interpretable. And while most matching methods don't handle large covariate spaces and don't aim to match almost exactly, our framework, almost matching exactly, does exactly that. It leverages machine learning and database tools. And so it's scalable, it's fast, it's accurate. And most importantly, it provides a toolkit for granular insights into the data that we study. And it allows us to get a much better feel for when causal claims can actually be made. Thank you.
Thank you. That was a really great talk.
Thanks.
Yeah, we really encourage more people to ask more questions. In the meantime, I wonder, is there a risk of eliminating a confounder?
I mean, there's always a risk of eliminating a confounder. But if it's not predicting well on the training set, if it's not really being used to predict on the training set, then, I
Right.
mean, if you're using something like Dame, you're going to match on it anyway if you can.
Right.
You could get variable importance completely wrong and match on totally the wrong variables, but that's better than sort of, not even trying to do this.
Yeah. No, I hear you. I was just wondering because of that one chart where you let it run to the end, which so you have the 5% tolerance in the one graph, and then you have the, I guess, no tolerance. Is that how we interpret the second graph? It can eliminate whatever it wishes.
The second graph is where you basically let it produce these really crappy match groups where you've eliminated all but two variables and you match whoever's left on those two variables.
Right.
We could have predicted that those wouldn't have been good matches. In fact, we did. We stopped early.
Yeah, totally. I was just wondering, because it looked like, so for each of those Kate estimates, you get sort of like a bias. You get more bias. You get biased estimates from many examples. And I was just wondering if that could be because it without that sort of safety 5% tolerance, then it could be more likely that it eliminates a confounder, possibly.
Yeah, so if you don't have that 5% or some tolerance at least, then you can be matching units on sets of covariates that really are not good enough. So not good enough to make a good, reliable Kate estimate. Right, because you're only matching on, say, two covariates, and you really need to match on this extra covariate. Like, you really should have matched on age, because these people are totally different on age, and yet you call them a solid match group.
Right. Cool.
Yeah. So I think I missed a couple of questions. Let's see here.
We've got hands up too. Should Shuyu, I could allow to ask? Oh, they put their hand down.
Oh, I missed one here from looks like Amin.
Oh, yeah.
Does Dame eliminate only one subset of the remaining variables, or is it repeated elimination of subsets similarly to Flame? So Dame knows what has already been eliminated, and it'll eliminate a subset of variables, but it'll put it back. It'll put all those variables back so that all those variables are allowed to be used at the next iteration of Dame. So it's not backward elimination. It's like, okay, let's use this subset, we'll put it back. Let's use this other subset, put it back. It's like that. Okay, let's see here. Sorry, let's see. Okay, I have a question on the speed of the algorithm. You showed that for a data set of 1.2 million 30-dimensional covariates, Flame takes roughly an hour. It's actually like an hour and a half to do the matching. Does this time include the time to identify the sets of important covariates? Yes, it does. That's the full run of the algorithm. From my understanding, the most important, and actually the reason why it's so quickly is because of that basic exact match that we have using the database queries. That runs very quickly. That's because years and years of work in the databases community have optimized database queries, and that's why we can do this. From my understanding, the most important component is the objective function to select theta. Have you designed or tried other forms of this function? Oh, maybe I already answered that with malts and AHB. Other ways to determine informative or not besides being predictive, or including other factors like having less missing terms. So there is another factor that I skimmed over when I was doing this. So the true algorithm has an option for covariate balance. So if you think ahead a little bit when you're running the algorithm, you might realize that eliminating this particular covariate will lead you at the next iteration to a really imbalanced data set. Like you might have very few treatment units left or very few control units left. And so you might want to consider that when you're figuring out which covariate to eliminate. And so we actually have a balancing factor in the code, and it's on an adjustable, with a trade-off term, like a constant trade-off term, and the user can actually adjust this factor to kind of look ahead and decide whether, they want which covariate they want to actually favor. Does that make sense? I hope it does. But in terms of other ways to determine informative or not being predictive, predictive is the only tool that we have predictive and balancing factor. Those are the only terms that we're really using other than sort of regularization, other than sort of, smoothness and regularization. Yeah. Let's see. And in terms of missing data, there's a couple different ways to handle it. So one way to handle missing data is, I think I said this, maybe I said this earlier, but one way to handle it is to not match on missing data. In that case, you just simply wouldn't match on a variable that's missing. But another option is to use something like mice, which is a way of filling in missing data, multiple imputation, something or other. And mice is pretty reliable in filling in missing data. The only problem is that when you're matching on filled in data, then the results become less interpretable because then you're matching on estimates that aren't actually in the data. So that really depends on your problem, which one you want to do. We only need to identify the important covariates once, then we can use it for all the test cases, right? No, actually, we don't do that because if variables are correlated with each other, then as soon as one variable vanishes, then another variable becomes more important. So we actually recompute the machine learning all the time. We have support for not redoing the machine learning continuously, like that you maybe only need to redo it every once in a while. That support has been recently put into the code, but figuring out exactly when to redo the machine learning and when not to is a future that if you wanted to work on that, I would be delighted, put it that way. That's an important problem that hasn't been quite figured out yet. Okay, what happens when covariates are highly correlated? If Dame picks a subset enough to predict well, can I know if it could have chosen differently? Okay, so if it could have matched on more variables, it would have, because that's the way that Dame works, because of its backward elimination, or it doesn't do backward elimination. It does this sort of, I keep forgetting what that's called, but it's, where you wouldn't eliminate a subset unless you've eliminated all subsets of that subset. If it could have matched on more variables, it would have. But it could always have matched differently. So matching is it's not robust in the sense that there are many different good matches that could be constructed for any given unit. And some of these matches would be arbitrarily chosen between. And I don't find that to be a problem, given that even linear regression has the same issues, right? If variables are highly correlated, you could easily shift the weight from one coefficient to the other. But some people have issues with sort of non-robustness, in which case you could try to force it to eliminate variables in a specific order to eliminate the non-robustness. But I personally don't seem to think I don't really think it's a problem if there's multiple different ways you can match. And if it's good, I mean, on the other hand, it'd be nice to know at some point, like if you have a relatively small data set and you're matching, it'd be nice to know kind of the extremes of treatment effect. Like if you match, let me say it. If I match one way, I could get this treatment effect. If I match the other way, I could get this average treatment effect. Like I would love to be able to find that information for like a small data set. So, you know, I actually have a separate paper on how to do that. But that's, you know, that's Flame and Dame work on these huge data sets. So hopefully you get kind of reliable results from them. And then we're also doing a lot of work on like variance estimation to try to figure out, you know, for a given Kate estimate, what's the variance on that estimate? And there's a couple of different ways to do that, which I don't really have time to talk about another day.
I think there was just one more follow-up in the chat, and then maybe we can wrap up and move on to our next meeting.
Okay. So Dame tries out all subsets for the remaining variables and then removes the biggest possible subset. No, it removes the smallest possible subset. It removes the least harmful subset, given the 5% error constraint, right? So it's trying to eliminate as few variables as possible so that you can match on more variables.
Thank you very much, Cynthia, for the talk, and thank you everyone for coming and for the great questions, and look forward to seeing you all next time. Cynthia, I sent the link in your email. Did you get the link for the next chat?
Yeah.